sort of equation for it. So can we talk about that? How much fence we're going to use? Well, how much fence will we use from here to here? We don't know, right? Let's call it x. Let's call the distance from here x, right? And then we can call the distance from here to here what? Y. Right? So can you tell me what the perimeter of that thing would be, or what the total linear fence would be in terms of that? I'm going to call it P, but what would it be? X plus 4y. The perimeter is going to be whatever that distance is, right? Plus 1, 2, 3, 4 of those. I would like to know the smallest this can be. Problem is, the perimeter depends on two variables. I need to get it down to one. What have I not used? The constraint, which is that each of these pins has to have an area of 200, right? Okay, so now the constraint. The constraint is that this one's a little tricky. It's like I've forgotten about these sticks over here. Marcus? Can you help me with the constraint? The area of each pin. Okay, good. Okay, I agree. The area of each enclosure has to be 200. Now, we're trying to get everything in terms of x and y, because if we can get that to have x's and y's in it, then we can come back and plug it in here. So can you tell me a little bit about the area of a single pen in terms of x and y?
1/4 x times y.
Perfect. 1/4 x times y. Does everyone see that? Be very careful. It's not x times y, because x is this whole distance, right? We've cut this into 4 equal pieces. So from here to here is 1/4 x, right? So 1/4 x times y must be 200. And just to make our lives a little easier, this is the same as saying x times y equals 800. Just multiplying both sides by 4. Clears out that fraction. Any questions? Good job, Marcus. Salo? Okay. What am I going to do with this? I have a constraint equation. It's a relationship between x and y, right? We're trying to get this in terms of a single variable, right? We have two variables in here, but I also have this relationship. So what can I do with this? Solve for y or x, right? It's your choice, but let's solve for y. So if I solve for y here, divide both sides by x, right? Okay. And now we can take this, right, and replace that over that y with that. So let's do that. So now our perimeter, I'm going to come up here and do this. Our perimeter will now be x plus 4 times y, but y was 800 over x. So our perimeter is now a function of x. Would you all agree? I've got just x's in there. So I'm going to switch it from p to p of x, and it's x plus 3200 over x. There it is. Luke? Okay, Luke. What's next? Almost. This is a critical step. Luke, on the final, don't forget this. Domain, right? So are we on a closed interval or an open interval here? You think it's closed? Okay, so what would be your restriction on x then? What's the smallest x could be then if it's closed? So x is distance from here to here, right? So what do you think it would be? Smallest. 0. Okay, so what do y'all think? Look at your function, Luke. Can you plug 0 into this? You can't. See, you have division by 0. In fact, if you come back and look at your constraint right here, you can't plug 0 in for x. This problem, for the first time, we can't do a closed interval. And the reason why is because, look, in the previous problem, we had a fixed amount of fence, right? They gave us 100 feet of fence. We could make that 0 if we wanted to. Here, we have to have a fixed what? It's gone. A fixed area, right? And the only way you can ever get area is if one of the sides, that both sides have to have a length to them, right? So it'd be impossible for us to make one of those sides 0 and still have 200 square feet. Okay? So this is very subtle, but it's very important. At this point, we know that x can't be 0, but it can be really small, right? Yeah. So I'm going to have to do an open interval here. I'm going to have to go 0. 0 to what? How big can x be? Infinity, because now it wouldn't make sense physically, right? And the river is not straight forever, but it's more. This is more of a theoretical problem. I mean, you could have a fence here that went out like 1,000 feet, right? And then this y would be like nothing, you know? And you couldn't put any animals in there, right? But let's go with the whole distance. The other thing I should mention is you can't tell me it's 400 or something like that. You can't give me a point to stop at. There's no like nice number that you can just pick. So we're just going to go the whole way out. And let's just see what happens on this interval. But now our method changes, doesn't it? Our method changes. So we have to take derivative of that. Let's do that. So open interval. 1 minus 3,200 over x squared. So derivative of x is 1. Remember, this is x to the negative 1, right? So when we do x to the negative 1, we bring the negative 1 out, and then we subtract 1, so we should get this. What are we going to do with this? Set it equal to 0. Okay, so let's take that derivative, set it to 0. That means we're going to set 1 minus 3,200 over x squared equal to 0. And this, there's a couple of ways to go about this. I'm just going to move everything that's negative to the other side. Bless you. And then I'm going to multiply both sides by x squared to get the fraction to be gone. X squared here, x squared here. And now I'm going to take the square root on both sides. And I should get plus or minus, right? Square root 3,200. However, I can throw out the negative answer, right? Because I'm only looking at positive x values. So really, my only critical number here is square root of 3,200. Yes, that could simplify, and we could get it as a decimal and all that good stuff. But I'm just going to leave it like that right now. Any questions? Danielle? Where's Danielle? I don't think she's... Oh, Danielle, yeah, used to be right there, I think, yeah.
How did you get that derivative?
How did I get the derivative? Okay, so this is good, right? Okay, this right here is 3,200 x to the negative 1. And then brought the negative 1 out, and then subtracted 1 from that, and then dropped it back down. Good? Okay, how about, mix these up. Annika. Okay. I don't even know what I'm asking you. Yeah, what's the next step? Okay, good. Good. So we've figured out where the derivative is 0, right? Now where's the derivative not exist? And what do you think? At 0, right? But 0 is not in the domain. So it's not a critical number, but it is a critical number, but it's not, but it is. We've been through that mess before. So at 0, the derivative is undefined, right? Derivative is undefined there, but it's not in our domain. Okay. So you want to keep going? What would happen after this step? We've got our critical numbers, right? Number line, see? So now we're in a different method. We have to do a number line now. Okay, number line, and what's going to go on this number line? 0. And then that thing right there, root 3200, which I know is positive, right? So I'm just going to put it over here. And that breaks up my number line like this. Right? Everyone good? But I'm not going to look over here at all. I'm not going to pick any test points over there because I'm not allowed to look to the left of 0 because that's not in the domain of the original function. So I just need to grab 2 test points here and here. And see, David M. Hey. So, test point, what would you like? Your choice. You have any number between here and here. 1, I love 1. 1 is great. 1's easy to work with, right? And then any number over here. You know what? You know an easy way to do this one? If this is the square root of 3200, why not just 3200 then? That's definitely bigger than the square root of it, right? So I mean, I could pick 3200. See what I mean? That's kind of an easy pick.
Yeah.
Now what? Drum roll. Plug those into derivative, right? You can't get this messed up. You have to make sure you know the method you're using. So these points get plugged into the derivative, and the derivative is sitting right there. And remember, all we care about is whether or not we get a positive or negative answer out. So what is p prime of 1, and what is p prime of 3200? All right, let's go with p prime of 1. Plug 1 in here, right? Super nice to square that. You're going to get 1 minus like 3200, which is negative, yes? So this gives us a negative, which tells us our perimeter function is doing what here? It's going down. Our perimeter function is going down here. That's a great sign, because what were we looking for? We were looking for a minimum, right? This is looking very promising that we're going to have a minimum, right? We just need that side to go up. So if we plug in 3200 into the derivative right here, what would you get? It's going to be positive, okay? You can just plug it in yourself. You're going to get positive there, which means that our original function's going up. So is this a local minimum? Yes, because it goes down then up, and root 3200 is in the domain of the function. Now, how do we know that this is the only minimum we have? It's the only spot where we go down and up. It's the only place it happens, right? There's no other places where this happens. So this is the only minimum possible. So this is the one. All right? So conclusion is that P has a minimum at x equals the square root of 3200. Have we answered the question? What was the question? Find the dimensions of the pen, right? Of the enclosure, basically, that gives us the minimum area, or minimum perimeter, amount of fence used, right? This is not the dimensions. This is just x. What else do we need? We need y, right? So where we can get y from? Go back to your constraint. Remember that? We solved for it. Wasn't this y? Wasn't that y? Remember that? We solved for y way back when? So if that's what y is, and we can come over here and say it happens when this is that, and this is 800 over root 3200, because we know the x is this, right? So 800 over x. So if you go back and you look at the picture, we had the two rivers, and then we had our pins, right? Our pins went like this, right? We only built what was in the red, right? What we're saying is that this distance from here to here needs to be the square root of 3,200. And this distance from here to here needs to be 800 over the square root of 3,200. Just going to see what those are as decimals here. I'm sure some of you have already done it. So this is about 56.56, and then 800 divided by that is about 14.14. So if you build it this way, you will have achieved an area for each pen of 200 square feet, and you will have used the least amount of material possible. Right? Okay. We've got more time. I think I'm trying to gauge whether or not we have enough time for the next problem. We do. We're just kind of scratching the surface here. There's still lots of different variations of problems like that we could have here. I like this next one because it's applicable to the real world for sure. Let's say that we want to construct a can made out of aluminum. An aluminum can, right? And what we need is so that this thing needs to hold 1 liter. And a liter, just for our information, is 1,000 squared cubic centimeters. So a centimeter, right, is pretty small. So if you take a little block that's a centimeter by a centimeter by a centimeter, 1 liter contains 1,000 of those, all right? That's what a liter is. So we're trying to build this thing, right? And the company, right, oh, here we go. Got one right here. Cute little can. Aluminum. This aluminum costs money, right? So I want to build this in a way that I use the least amount of material, right? Like this thing holds 8.4 ounces, 250 milliliters. That's what this holds. But we need to build a can that holds 1 liter, but we want to use the least amount of material. So let's see if we can't decipher that into a problem here. Herman, any ideas? You understand the question yet?
Kind of.
Are we trying to maximize something or minimize something?
Minimize.
Minimize what?
Material.
The material? Okay, what's another word or words you would use for the amount of material used? Is that a length? Is that an area? Is that a volume? What is the amount of material used?
Volume.
Okay, so volume is a 3-dimensional thing, so it's the amount of stuff inside of a container, right? That's the stuff inside. We already know how much stuff has to be inside, right? That's how much stuff has to be inside. We want to use the least amount of material, which is going to be the outside surface of the thing, right? Of the can.
So it should be area.
It's area, right? So we want to minimize the area. More specifically, the surface area. You all agree, we want to minimize the surface area. All right, well, let's see if we can't come up with well, I shouldn't have said that, damn it. Al, what do we need to do? We want to minimize surface area, so we need to come up with a objective function, right? So what is the thing we're trying to minimize? Surface area. So we need something that gives us the surface area of a can, right? A can. So let's see if we can't come up with the formula for the area, surface area of a can. Yes?
Would it be 2 pi r squared plus 2 pi r h? So like the surface area of the two tops, and then like the circumference times the height.
That sounds right. You said 2 pi r squared plus
2 pi r h.
2 pi r h. Yeah, that's right. Good. So let's all go through that. Okay? So if this is a can, right? This can has a radius to it. We don't know what it is, do we? We don't know the radius of this can. So, but if we did, right? If we knew the radius and we knew the height, then we should be able to figure out the surface area. Was there a formula? I don't know. Al, did you look in there? We don't need it, but I was wondering if you found a formula. Okay, so the way we're doing this, David, you just did, I'm going to find the area of the top and the bottom of the can first, right? So the area of that will be the top of the can, which should be pi r squared. Agreed? That's the area of the top of the can. Area of the bottom of the can, which is another pi r squared. And then you have to find the area of the surface going around the can, right? And the way you can imagine that is by just imagine cutting this thing open, right? And laying it flat. So it's like we have a can like this, right? We want to know the surface area around it, so we cut it and we lay it open. When we lay it open, we got this shape, right? So if we take that shape, how tall is it? H, right? Now, we need to know this distance from here to here. And where did you get that from, David? That's circumference. So when you cut this, right, and you lay this open like this, the distance from here to here is also the circumference of the circle to begin with, right? So if we know the circumference, that's this distance, and the circumference by definition is 2 pi r. So that's where you got that from, right? 2 pi r? So the area of this, which is the area around the can, is those two multiplied, 2 pi r h. So the total surface area of the can is 2 pi r squared plus 2 pi r h. Jesse is not here, I don't think. Yusef? I'm letting you catch up. Is this making sense so far?
Yes.
Okay. So we have this, right? This gives us the area. We want to try and find a way to minimize this, make it as small as possible. How many variables are in here right now? 2, r and h. In order to use calculus, we need to get it down to what? To one variable, right? To one variable. So we need some sort of what now? What have we been, this thing on the side that I've been doing that's allowed us to get everything down to one variable? We've called that the what?
Constraint.
The constraint, okay. So Yusef, do you see a constraint here? What constraint do we have in this problem? There's one, yeah, the what?
1,000.
Yeah, 1,000 cubic centimeters. That's the volume of this thing, right? We know that the volume of this has to be 1,000 cubic centimeters. Now, do we know what the volume of a can is? So what's the volume of this can? So how do you find the volume of this? You take the area on top, pi r squared, and you multiply it times how deep it is. So it's like that area stacked up a bunch of them, h of them, right? Now that is a formula in your notes or in your formula sheets, but I'm just going to put it here. This is pi r squared h. That's the volume of a can, and that must be 1,000. I'm going to get rid of the cubic centimeters for now. I'm just going to work with the number 1,000. All right, that makes sense?
Yes.
Okay, so now what should I do with this?
Gotta get it down to one variable, so you move.
Yeah, so what do you want? You want to solve for h or you want to solve for r here? What looks easier? R, so if I solve for R, I've got to get rid of the pi and the h, right? And then I have to take a square root. Do you want to do that? Or do you want to solve for the h, which would just be divide by pi r squared? We can go both ways. You don't care? You pick. H or R? H? Do you see why H is easier? Yes? Yes? H? Everyone's like, H. But do you see it? Why it's easier?
Oh, yeah.
Okay, good. So pi r squared. All right, so now what we're going to do, everyone was like, don't say R, don't say R. It would have been messy, but we could have done it still. This is still going to be messy, but all right, so now we got, our constraint has given us a way to relate H and R together. I'm going to take that H and I'm going to plug it in up there for that H right there. That's the only H in the whole problem, right? So I'm going to have my area is now a function of R, because I know on the next line everything's going to have R's in it. I've got 2 pi r squared plus 2 pi r, and then h, which is 1,000 over pi r squared. Everyone see that h? Pardon? Yeah, we're going to start to get some things to cancel. So this is actually going to work out to be somewhat nice. This pi, that r, and one of those r's. There we go. Okay, so our surface area function of R is 2 pi r squared. All right, still have the 2, still have 1,000, right? So 2,000 over R. Not bad. Owen? Yeah, no go. Jasmine? Ronnie? What's the next step, Ronnie? Nope. Domain. Okay, so now, twice this has happened. I think this has happened 3 times. I've heard derivative 3 times when I asked for this step. Be very careful, right? Because you can really get lost in a problem like this if you don't do domain. Remember, the domain is going to dictate what method you're using. So if you don't do this step, then what method do you do, right? I should also point out, I'm running short on time here, but remember in the last problem when we were doing it, we got like, okay, P is going down and then P was going up? Yes? Wait a minute, no. Yes, that's what we did, right? And we had this? Okay, but I actually had to go in and plug these test points in to show the down and up. A lot of times on the final, what students will do is they'll set the derivative equal to 0 and they will get root 3200. But they will never show the down and up. And they'll say the answer is root 3200, which it is. But they never showed it was a minimum. They just assumed it was. So you have to go through this process of this down up thing. All right? Just don't forget that when you're doing problems. All right, okay, so back to here. Ronnie, domain. Okay, so with domain, Ronnie, our variable here is R, right? Is there a smallest value R can be? So R is the radius of the can, isn't it? Right? So is there a smallest that R can be? 0? Okay, now look at your function. Can you plug 0 into your area function? No. So you can go real small with the radius, but you can't be 0, which automatically says we're now open interval. Okay? And I'm going to go 0 to infinity. I mean, it would be ridiculous to have this infinitely wide can, right? And you walk in with this big wafer, right? And you're like sipping out of this. It's like really short, wide can. Okay. But we're going to take every possibility into consideration, right? All right, so here we go. Derivative time now, right? So we take our derivative, and that's going to be 4 pi r. So that's just power rule. That we kind of just did that one a second ago, didn't we? Like that sort of 2,000 over r. That should give us negative 2,000 over r squared. And we've got to set this thing to 0 now, right? Setting this thing to 0. What should we do here to solve that one? Combine them together. So in the last problem, this turned out to be, this was like 1 and 1 and then this other term, we just moved it over. The reason I'm not doing that now is because this has an R in it. So I'm going to put these together, all right? So put them together. We've got multiply. So this is over 1, so we have to multiply top and bottom by R squared. So 4 pi R what? Cubed. Minus 2,000, that's our new numerator, over R squared. That must be 0. And a fraction can only be 0 when the numerator is 0. So you look at this only. And that we can solve for R cubed, just manipulating things around, right? 4 pi R cubed equals 2,000. Divide both sides by 4 pi. (500 over pi). And lastly, take the cube root. We have a critical number when R is the cube root of 500 over pi. I'm going to go ahead and get that as a decimal real quick. Maybe. It's approximately, raised to the 1 divided by 3. 5.41. We'll go with approximately 5.42, okay? 5.42. What's next? Number line. Yeah, does it ever not exist? Does this derivative never not exist? At 0, but 0 is the left endpoint, so we will consider it, but not really. This is almost exactly like the previous problem. So we're going to just do a number line now. We're going to put on this number line 0, and we're going to put 5.42. It's going to break our number line up into 3 regions. We're going to ignore everything to the left of 0. We're going to pick a nice test point right here, like the number 1, and then anything to the right of 5.42. 6, okay, 6. And where are those going? Into the derivative, right? So we want a prime of 1, we want a prime of 6. And we're looking to see if it's positive or negative. So if we do a prime of 1, let's see. We get 4 pi minus 2. Oh, wow, that's going to be negative. It's pretty, I hope that's obvious. 4 pi is like 12, maybe 13, minus 2,000. So you get negative here. So our area function is going down here. Good, because we're looking for a minimum, right? And if we plug in 6, a little harder to see with 6. Check this out. Just check this out. Couldn't I have picked a number like 6 was fine, but couldn't I have picked like infinity almost? The idea of infinity, something way out there. Think about what happens to the derivative if you were to like think of R as being infinite. This would become what? Infinite, and that would go to 0. So you'd have something positive infinity, right? So without even plugging a number in, you can see what's happening way out to the right. It's positive though. So that means our original function is going up over there. Looks like we found a local min, right? It's happening when A is, yeah, now I never said find the dimensions or anything like that, right? So let's just find the dimensions of this can. We know part of it already, right? We have a minimum area, surface area, when the radius of the can is about 5.42. If we wanted to be exact, It's actually the cube root of 500 over pi, but we're doing some approximations here. We have a minimum here. Now, what was the other part of the can that we should find if we're going to look for its dimensions? The height, okay? So the height, what was the formula for height? Somewhere in the back, somewhere we had solved for height. It was 1,000 over what? Pi times the radius squared. Yes? Oh, check this out. It was pi times the radius squared? Okay. Yeah, well, let's do it as a decimal first. 5.42 squared. So somebody do that on their calculator. 1,000 divided by pi times the radius squared. This is going to be somewhat amazing. Your answer is going to be somewhat amazing.
Comes to 10.83.
10.83 approximately?
10.84.
10.84. Okay? So if we want to make a 1 liter can and use the least amount of aluminum or surface to do it, then we should have a can that has a radius of what? 5.42 and a height of what? 10 point, what? Hey, ooh, wait a minute. 10.84? Wait a minute. Isn't 10.84 double the radius? So aren't you, or is that really saying to us that the diameter of the can has to be the height of the can? That's exactly what it's saying to us. So watch, right here. You see this step right here? This step? Okay, for this step, if I were to do 1,000, I still have 2 minutes. Pi, and instead of doing the decimal, I plug in cube root of, what was it, 500 over pi? But then take that and square that, right? That's what it technically is. Watch what I get if I actually do this. Okay, so this is 1,000 over pi times 500 over pi. That's raised to the 2/3. Do y'all agree with that? The cube root of something and then square is this. Yeah? Okay, so now watch this. This is 1,000 over pi times 500 to the 2/3 over pi to the 2/3. Agree? Just 2/3 on both? And now look at these. This is like, that one's on top of that one, right? So what happens if I take pi to the first power and I divide it by pi to the 2/3? I get pi to the 1/3. Yeah? Pi to the 1/3? I'm going to run out of room. Pi to the 1/3, pi to the 1/3. So I have 1,000 over pi to the 1/3, and then 500, right? Let me do it this way. Yeah, 500 to the 2/3, right? That. Trying to show you. Let me do it this. 100 over pi. I'll do cube root of pi and then times cube root of 500 squared, like that. Is that the same thing? Okay, so this is 1,000 over cube root of 500 squared times pi. I just put them both underneath. Yes? So what now? What's 500 squared? What am I, there's something I'm missing. I'm trying to get to the point where h should be double this. It should just be 2 times this. This should turn out to be 2 times this. Okay, let's do this. I'm going to multiply this by, I'm going to run out of time, damn it. Okay, 500 squared on the bottom So what would happen if I do that? On the bottom, what would I get? If I do the cube root of this, then times the cube root of that squared, then that should just be on the bottom 500 squared times pi, right? And on the top, I get 1,000. I'm out of time. We can clean this up more. I'll finish it next time, maybe. I have to stop because I have something else I need to tell you. The big picture of this problem is that if you're manufacturing cans and you want to use the least amount of material, then what you're going to do is you're going to make the diameter or diameter of the can equal to the height of the can. And that's the cheapest way to do it. So why does this look like this then? Why did I not make it the diameter and the height the same? The reason is because this is not a true cylinder. Like, they have to account for that little dip in the bottom, right? Okay, that's in case it gets overpressurized, so that will pop out. They also have to, this is not flat on the top, right? They have to account for how much it costs to make that tab. Everything has to be taken into account. And then there's like the aesthetic coolness factor of the can too, right? Like this can just looks pretty cool. But they definitely take into consideration that someone in this company has optimized a function. I guarantee it, all right? They said, we need our can to have these sort of things. You know, this is the cost of everything, optimized, and they found the dimensions that worked and were aesthetically pleasing, and that's what they went with. You know? Yeah? All these things have to be factored in. But if you truly make a true can, if you look back to like, y'all can pack up. If you look back to like the 1950s, when we were manufacturing like canned goods, the ones that you just like, you have to have the can opener to go around the edges, like oil cans, old food. Most of those cans were built so that the diameter and the height are the same. And that's because of this problem. They've optimized it. Okay, we will do more examples when we come back on Thursday. More optimization. We're spending 2 days on this. All right? And then we get into chapter 5, antiderivatives. Start getting us ready for Cal 2. Have a good one.